Assalamu alaikum. Bismillahirrahmanirrahim. I welcome you to the 44th lecture for the series of lectures on advanced computer architecture. Today we will be having a number of case studies while putting it all together what we have been discussing in our earlier 43 lectures. While discussing different cases of the computer architectures, we will be discussing the design and architecture of advanced computers, particularly the PowerPC series 750 and 970 architectures. We will also be discussing the case of Intel Pentium 6 architecture and Titanium architecture. So let us have a start with the PowerPC 750 architecture. The general introduction about the PowerPC 750 can be given by introducing this microprocessor as the advanced family member of the RISC, that is reduced instruction set computers microprocessor series. This microprocessor is basically a 32-bit portion of the PowerPC architecture, which provides 32-bit effective addresses for integer data of 8-bit, 16-bit and 32 bits, whereas for the floating point data of type 32 bits and 64 bits. It is a high performance superscalar microprocessor architecture that has 6 execution units and 2 register files. It can fetch for the instruction cache as many as 4 instructions per cycle, and it can dispatch up to 2 instructions per cycles and executes up to 6 instructions per clock. Let us have a look onto the instructions of PowerPC 750 microprocessor. The instructions of PowerPC 750 are encoded as single word of 32 bits. The instruction formats are consistent among all instruction types, permitting efficient decoding to occur in parallel with the operating access. That is, the operand access and the instruction decoding takes place simultaneously. This fixed instruction length and the consistent format greatly simplifies the instruction pipelining. This we have already studied in detail when we talked about the pipeline architecture. Integer instructions are the integer arithmetic, integer compare, logical, rotate, and shift instructions. The floating point instructions are the floating point arithmetic, multiply, add, rounding, and conversion. Also, the floating point compare, status, and control instructions. Whereas the load store instructions include integer and floating point load and store. It also includes the atomic memory operations. The flow control instructions contain branching, condition register logical and trap, and the other instructions that affect the instruction flow. The PowerPC instruction set architecture also includes the processor control instructions. These instructions are used for synchronizing memory accesses and management of caches. Also for using the translation look-aside buffers and the segment registers management. The instruction set also include the memory control instructions. These instructions are provided for the control of caches, the translation look-aside buffers, and segment registers. Here you can have a look onto the overall block diagram of the 750 PowerPC. Here you can see that it has got different sections which are used for the branch instructions, for the processing of if operation, and then there is a register dispatch and rename buffer section. It also includes the caches of level 1 and level 2. And then it has got a data cache interface connected, which is shown at the bottom end. Now let us talk about the instruction flow. The instruction flow of PowerPC includes instruction fetch, instruction decode, and instruction dispatch. The instruction flow in PowerPC is illustrated here in this block diagram. Here you can see that the PowerPC 750 allows maximum 4 instruction fetches per clock cycle. However, the number of clock cycles necessary to request instructions from the memory system very much depends on where exactly the instruction is. That is, where the branch target instruction cache is, or whether it is on the on-chip instruction L1 cache or on L2 cache. Now, having understood the instruction flow, let us discuss how the PowerPC 750 decodes and dispatch instructions. In order to discuss this concept of decode and dispatch, have a look onto the instruction flow diagram shown over here. Note that here the instructions can be dispatched only from the 2 lowest instruction queue entries, that is the IQ0 and IQ1. Moreover, a maximum of 2 instructions can be dispatched per clock, although an additional branch instruction can be handled by the branch processing unit shown here as BPU, but the maximum number of instructions is 2. Moreover, only 1 instruction can be dispatched to each execution unit per clock cycle. Also note that to facilitate dispatch, there must be a vacancy in the specified execution unit, and a rename register must be available for each destination operand specified by the instruction. Furthermore, there must be an open position in the completion queue, because if no entry is available, the instruction remains in the instruction queue. Now, let us have a look onto the superscalar pipeline architecture of the PowerPC 750. Here you can see that It contains two integer units, IU1, that can execute any integer instructions, and IU2, which can execute all integer instructions except multiply and divide. Here you can see that these integer units share 32 general purpose registers for integer operands and a single entry reservation station for each. Furthermore, you can see that there exists one 3-stage floating point unit named as FPU. It allows both single and double precision operations. We have already discussed in detail the single precision and double precision operations. It also contains 32 64-bit floating point registers for single or double precision operands. Continuing our discussion onto the execution units, we note that the 2-stage load store unit contains 2 entry reservation stations, single cycle pipeline cache access, and 3 entry store queue. It supports both the big endian and little endian mode. Moreover, its dedicated adder performs the extended addition calculations, and it performs alignment and precision conversion for floating point data and sign extension for the integer data. Whereas the completion unit is one which retires an instruction from the 6-entry reorder buffer, which is called a completion queue. However, it retires this only when all instructions ahead of it have been completed and the instructions has finished execution and no exceptions are pending. The completion unit generates sequential program model. In this particular case, we can say that it is a precise exception model. The completion unit also monitors all dispatched instructions and it retires them in order. It keeps track of the unresolved branches and it flushes instructions from the mispredicted branches, and it retires as many as 2 instructions per cycle. Now let us see what is the PowerPC 750's rename buffer. The 750 provides rename registers for holding instruction results before the completion commits them to the architectured registers. Now here, if we refer to the instruction flow diagram which we showed you earlier, and it is shown here again, you can see that there are 6 general purpose registers which are used as rename registers. There are 6 floating point rename registers, and there is 1 each for CR, LR, and CTR. Furthermore, when an instruction is dispatched to its execution unit, a rename register for the result of that instruction is assigned. Here, the dispatcher also provides a tag to the execution unit identifying the rename register that forwards the required data for an instruction. When the source data reaches the rename register, execution can begin. The results are transferred from the rename registers to the architectured registers by the completion unit when an instruction is retired from the completion queue, and the results of squashed instructions are flushed from the rename registers. So now let us discuss the branch prediction unit. The branch prediction unit offers features both for the static branching and the dynamic branching. The static branch prediction is defined by the PowerPC architecture, and it involves encoding of the branch instructions. The PowerPC architecture provides a field in branch instructions. This is known as the BO field, and it allows software to hint whether a branch is likely to be taken or not. Here, rather than delaying the instruction processing until the condition is known, 750 uses the instruction encoding to predict whether the branch is likely to be taken, and it begins fetching and execution along the path. Now let us see how the PowerPC 750 deals with the dynamic branch prediction. For dynamic branch predictions, the PowerPC 750 uses 512 entry branch history table with 2 bits per entry, and it allows prediction as not taken, strongly not taken, taken, and strongly taken. So with this much discussion about the static and dynamic branch prediction in PowerPC 750, let us talk about the branch target cache. The 750 uses branch target cache to reduce time required for fetching target instructions when branch is predicted to be taken. The branch target instruction cache has 64 entries, that is 16 sets, 4-way set associative organization, and the cache for branch instructions have encountered in branch loop code sequence. The branch target instruction cache hit means that the instructions are fetched into the instruction queue as a cycle sooner than it can be made available from the instruction cache. The PowerPC 750 also allows the multiple branch prediction. The 750 executes through 2 levels of prediction. One, the instructions from the first unresolved branches can execute, but they cannot complete until the branch is resolved. If a second branch instruction is encountered in the prediction instruction stream, it can be predicted. Moreover, the instructions can be fetched but not executed from the second branch stream. No action can be taken for a third branch instruction until at least 1 or 2 previous branch instructions have been resolved. Now let us have a look onto the working of the 750 cache. The 750 PowerPC has separate on-chip instruction cache and data cache. These caches are 32K byte 8-way set associative instruction cache. It is using the pseudo least recently used replacement policy, and 32 byte 8-word cache block, physically indexed and physical tags. Moreover, the cache write back or write through operations per clock are being used in this design. The caches here can be disabled in software as well as they can be locked in software. The data cache coherency follows MEI for the maintenance in the hardware, and the critical double word is made available to the requesting unit. The cache is also non-blocking. Now let us see what is the organization of data cache and the instruction cache. The data cache, as you can see from here, is organized as 32-word block cache, and there are 128 sets with 20 bits tag, and it is using the state MEI. Whereas the instruction cache is also 32-word block, and it is also having 128 sets, 20-bit tags. However, it is using valid, not valid bit instead of the state information, and it is not snooped. The PowerPC 750 also allows multiprocessing. The 750 multiprocessing support features include: number one, the hardware enforcement, and number two, the load store. The hardware enforcement is achieved by using 3-state cache coherency protocols for the data cache, and the load stores are used with reservation instruction pairs for atomic memory references, semaphores, and other multiprocessor operations. The 750 3-state cache coherency protocol MEI supports M for modified, E for exclusive, and I for invalid states. The state diagram for the cache coherency in case of PowerPC 750 is shown here in this diagram. Now, with this much introduction and the detailed study of the PowerPC 750, let us consider the other advanced microcomputer, that is the PowerPC 970FX. The overall organization of the PowerPC 970FX is shown here in this block diagram. It is vector, single instruction, multiple data stream, multimedia extension architecture. It is deeply pipeline design, which consists of 16 stages for most fixed point register operations, 18 registers for most load and store operations, and up to 25 registers for floating point operations. Here the VALU and 19 stages for vector permute operations are available. Furthermore, it allows dynamic instruction cracking for some complex instructions which are broken into two simpler or more RISC-like instructions, and it also allows simple inner core data flow. Now let us have a discussion onto the general features of 970FX PowerPC. It has got aggressive branch prediction features, that is, the predictions for up to 2 branches per cycle are allowed, and it supports for up to 16 predicted branches in flight, which means when there are 16 predictions or the predicted branches, they may be in operation at a time, and the prediction supports for branch direction and branch addresses. Moreover, the other feature of the 970FX PowerPC are that it has got in-order dispatch of up to 5 operations into distributed issue queues structure and out-of-order issue of up to 10 operations into 10 execution pipelines. Furthermore, it has got 2 load or store operations, 2 fixed point register operations, 2 floating point operations, 1 branch operation, 1 condition register operation, 1 vector permute operation, and 1 vector ALU operation. The other features are that it facilitates register renaming, and the cache coherency protocols are MERSI, means that it is a 5 states cache coherency protocol, which is modified, exclusive, recent, shared, and invalid. The further features are that it has got large number of instructions in flight. Theoretically, it can have in flight up to 215 instructions, which is a very large number, and it allows up to 16 instructions in the instruction fetch unit and up to 32 instructions in the instruction fetch buffer in instruction decode unit, and up to 35 instructions in the 3 decode pipe stages and 4 dispatch buffers, and moreover it allows up to 100 instructions in the inner core, that is after the dispatch, and up to 32 store queued in the store queue, that is the ST queue, and it has got fast selective flush for incorrect speculative instructions and results. The specific focus is on the storage latency management and the out of order and speculative issue of load operations, and it also supports for up to 8 outstanding L1 cache line misses. It has got excellent features. For example, the additional features are that the hardware initiated instructions prefetching from L2 cache and the software initiated data streams prefetching with support for up to 8 active streams and critical word forwarding and critical sector first conditional operations and new branch processing and prediction hints for branch instructions are allowed over here. Now, with this much general introduction about the features of the 970FX PowerPC, let us see how the instructions are fetched and then the other steps are taken. Here, the 64 kilobyte direct mapped instruction cache, that is the I cache, is used, which has got 128 byte lines which are broken into 4 32 byte sectors, and it has got dedicated 32-byte read-write interface from L2 cache and with critical sector first reload policy. Moreover, in PowerPC 970FX, the performance of instruction fetch is enhanced by using a 4-entry 128 bytes instruction prefetch queue. This instruction prefetch queue is above the normal instruction queue and it is hardware initiated. Moreover, the fetch of 32 bytes is aligned for a block of 8 instructions per cycle. Now, getting the information about how the PowerPC fetch the instruction, let us discuss how its branch prediction works. In PowerPC, it scans all 8 fetched instructions for branches each cycle. So it fetches 8 instructions and all these 8 instructions are scanned for branches. The facilities available over here are to predict up to 2 branches per cycle. It has got 3-table prediction structure where these 3 tables are corresponding to the local, which has got 16 entries, 1 bit each for taken, not taken. The second is the global level, which is also having 16K entries, 1 bit each, and 11-bit history. Whereas the third one is the selector type, which has got 16 entries, 1 bit each, indexed as above, and it uses the local predictor and it uses the global predictor concept also. These concepts we discussed earlier in details when we talked about the branch prediction concept. This combination of branch prediction tables has been shown to produce very accurate prediction on a wide range of workload types. Furthermore, 16-entry link stack for address prediction with stack recovery predict the target address for a branch to link instructions that it believes corresponds to a subroutine return which is pushed into the stack earlier. And the 32-entry count cache for address prediction, that is the index by the address of branch conditional to count branch instructions. Now, after talking about the branch prediction, let us see how the PowerPC 970FX decodes the instructions and it performs the pre-processing. Here, the 3-cycle pipeline is used to decode and pre-process the instructions. The pre-processing of instructions involve cracking of one instruction into 2 internal operations. The cracked and microcoded instructions have access to 4 renamed emulation general purpose registers, 1 renamed emulation floating point register, and 1 renamed emulation CR field. Furthermore, it has got 8 entry instructions fetch buffer, which is having up to 8 instructions in 5 instructions out each cycle. Moreover, for instruction dispatch, there are 4 instruction dispatch buffers. These buffers can hold up to 4 dispatch groups when the global completion table is full, and there are 20 entry global completion tables where these are group-oriented tracking associated, a 5 operation dispatch group, and it tracks the internal operations from dispatch to completion for up to 100 operations. Furthermore, this process is capable of restoring the machine state for any of the instruction in operation. Very fast restoration for instructions on group boundaries, that is the branches, is performed, and it is slower instructions contained within a group. Moreover, the instruction dispatch and completion supports the precise exceptions. Now, let us talk about the branch condition and register execution pipeline in 970FX PowerPC. Here in this structure, there is one branch execution pipeline which computes actual branch address and branch direction for comparison with prediction. It redirects the instruction fetching if either prediction was incorrect, and finally it assists in training and maintaining the branch table prediction, the link line stack, and the count cache. Furthermore, the executive CR logical instructions and the movement operations are performed over here, and it executes some more to or from special purpose, general purpose instructions also. Furthermore, in the branch prediction and branch execution, the out of order issue with bias towards the oldest operation first is performed. Now let us talk about the data stream prefetch. For data stream prefetch, 8 data prefetch streams are used which are supported in hardware. 8 hardware streams are only available if vector prefetch instructions are disabled. However, 4 vector prefetch streams supported use 4 of the 8 hardware streams, and the vector prefetch mapping algorithm supports the most commonly used form of the vector prefetch instructions. Now, this is in fact all about the PowerPC 970FX. Here we have observed that this particular microprocessor is using all those concepts for instruction fetch and branch predictions which we have studied in detail in this course. Now let us have a discussion onto the Intel family. For this, we will first of all have a look onto the Intel Pentium 6 microprocessors general architecture. The Pentium 6 family of processor is the generation of processors that succeeded the Pentium line of Intel processors. The Pentium 6 family implements Intel's dynamic execution microarchitecture, which includes multiple branch prediction, data flow analysis, and speculative execution. You can have a look onto the 3-engine and interface with the memory over here in this block diagram. Here you can see the major units are the fetch decode unit, the dispatch execute unit, and retire unit. The fetch decode unit is an in-order unit that takes as input the user program instruction stream from the instruction cache, and it decodes them into a series of micro operations that represent the data flow of the instruction stream. And moreover, it performs prefetch as speculative. The dispatch and execute unit is an out-of-order unit that accepts the data flow stream, schedules execution of the micro operations subject to the data dependencies and resources available, and temporarily stores the result of these operations and their execution. The retire unit is an in-order unit that knows how and when to commit, that is, when to retire the temporary speculative results of the permanent architectural state. There is another unit over here which is referred to as the bus interface unit. The bus interface unit communicates directly with the level 2 cache, and it supports up to 4 concurrent cache accesses. Moreover, the bus interface unit controls a transaction bus with MESI snooping protocol for coherency for the memory system. Now let us see what is inside the fetch. Inside the fetch unit, the level 1 cache fetches the cache line corresponding to the index from the next instruction pointer, and it presents 16 aligned bytes to the decoder. The decoder converts the Intel architectural instructions into the micro operations. These micro operations are 2 logical sources and 1 logical destination per micro operation. Most Intel instructions are converted directly into single micro operation, and some instructions are decoded into 1 to 4 micro operations, and complex instructions require microcodes. The micro operations are queued and sent to the register alias table, that is RAT unit. In the RAT unit, the logical Intel architectural based registers references are converted into references to physical register. That is, the logical references are converted into the physical references in the Pentium 6 family processors. Physical register references are being used. The micro operations are entered into the instruction pool, and the instruction pool is implemented as an array of concurrent addressable memory, which is also called the reorder buffer. Now let us have a look onto the dispatch and execute section for the Pentium 6. The dispatch unit here selects the micro operations from the instruction pool depending upon their status. If the status indicates that a micro operation has all of its operands, then the dispatch unit checks to see if the execution resources needed by the micro operation are also available. If both are true, then the reservation station removes that micro operation and sends it to the resource where it is executed. Furthermore, in the dispatch and execute unit, the results of the micro operation are later returned to the pool, and there are 5 ports on the reservation station, and the multiple resources are accessed. The Pentium 6 family of processors can schedule in an out of order fashion at a peak rate of 5 micro operations per clock, 1 to each resource port, but a sustained rate of 3 micro operations per clock is more typically used. Here, note that many of the micro operations are branches, and it uses the branch target buffer, which correctly predict most of these branches. The branch operations are tagged in the in-order pipeline with their fall-through addresses and the destination that was predicted to them. But if mispredicted, then the jump execution unit changes the status of all the micro operations behind the branch to remove them from the instruction pool. So in that case, the proper branch destination is provided to the branch target buffer, which restarts the whole pipeline from the new target address. Now, let us have a look onto the retire unit of the Intel microprocessor Pentium 6. Here, the retire unit is also checking the status of micro operations in the instruction pool. Once removed, the original architectural target of the micro operations is written as per the original Intel architectural instruction. The retire unit must also reimpose the original program order on them. Furthermore, the retire unit must first read the instruction pool to find the potential candidate for retirement, and it determines which of these candidates are next to the original program order. Once it has done so, then it writes the results of this cycle's retirement into the retirement register file, which is abbreviated as RRF. The retire unit is indeed capable of retiring 3 micro operations per clock. Now, towards the last discussion onto the Intel Pentium 6 processors bus interface unit, let us see what is inside the bus interface unit and how it works. The loads are encoded into single micro operation. The stores therefore require 2 micro operations, one to generate the address and one to generate the data. These micro operations must later recombine for the store to complete. The stores are never performed speculatively, since we know that there is no transparent way to undo the stores. The stores are also never reordered amongst themselves. A store is dispatched only when both the address and the data are available and there are no older stores awaiting dispatch. A study of importance of memory access reorder concludes that the stores must be constrained from passing other stores for only a small impact on performance. Moreover, the stores can be constrained from passing loads for an inconsequential performance loss. Constraining loads from passing other loads or stores have a significant effect on the performance. Moreover, the memory order buffer allows loads to pass other loads and store by acting like a reservation station and reorder buffer. With this much discussion, we have studied 3 advanced microcomputer architectures, that is the PowerPC 750, PowerPC 970, and Intel Pentium 6. With this, we have completed our discussion on all topics of advanced computer architecture. Next time, inshallah, which will be the last lecture, we will review all concepts we have studied in our earlier lectures. So now I stop here and say you Allah Hafiz till next time. Thank you.